Hello, my name is Ryan Perella, and I will begin taking you through my Lab 2 video report. The purpose of this experiment is to compare position versus time graphs of real-world versus experimental motion of free fall through computational simulations and no drag versus drag scenarios, all in order to better understand how motion works. The fundamental principles of motion, which will be seen in this experiment, are Newton's second law, which states that the acceleration of an object depends on its mass and the amount of force applied, commonly seen as F equals ma. The velocity update formula, which says that V final equals V initial plus the net force times the mass, all divided by the change of time, delta t. The position update formula, which is the same except with the position instead of velocity and then velocity instead of force. And the force of gravity, which is equal to negative mass times gravity, or mass times negative gravity. And then the new force, which is the drag force, which equals negative b v squared times v hat. In order to show the free fall of an object moving slower than a rock, we dropped a eraser from the height of a table and then used the tracker software in order to track its movement over time. This eraser was light, and therefore it dropped slower than a rock, and it experienced drag and air resistance. We dropped it from the height of the table. The time between our tracker points is 0.033 seconds, and the graph is in the y position versus time, and this does include drag as it is a real-world experiment. In order to make a computational model to track this data, we assume that the gravity and drag are the only two forces acting upon the system. Also that the object started with zero initial velocity and that the object is relatively close to Earth's surface. That way we could use force of gravity equals negative mg. This is the computational model encoding which I use to simulate drag and an experiment in free fall that does include drag. As said earlier, we use the formula force of gravity, or the force of drag equals negative b v squared v hat. This is the graph that the computational model produced that did have drag included into it. And as we can see that the longer time goes on, the more steadily the slope increases on the position versus time graph. And this is the velocity versus time graph. And as we can see, velocity is a constant increase, and that is because there is a constant acceleration of gravity on the system. Here is another computational model to track a free-falling object and create a graph that should simulate a free-falling object. This computational data does not include drag and therefore should be slightly different than our simulation, which does include drag because it is one force less acting upon the system. Here we can see the position versus time graph for this simulation. While this is a more zoomed in time period, we can see that the slope changes at a slightly different rate compared to our other graph, which did include drag. And the one that did include drag would be more accurate to what happens in real life because it accounts for more of the forces that would act upon this eraser dropping in real life, such as what we did in our actual experiment. And this is the velocity versus time graph. Again, it has a linear slope because acceleration is constant in the system. It is a constant 9.8 meters per second downward, and that leads to a constant linear slope of velocity. However, it is a non-zero slope, and that is because the velocity increases as time goes on due to the acceleration of gravity on the eraser, especially when the system does not include drag force. Now, the analysis of the results. Over a short time period, the interval does not diverge much between the slopes of the simulation that did include drag force and the simulation that did not. However, over the longer time period, this interval will have more variation, and that is due to more time passing, allowing the forces and acceleration to take more effect upon the system. Also, terminal velocity is when the drag force becomes equal to the gravity force, and that is the max speed that objects can fall at. Once they reach terminal velocity, their velocity does not increase anymore. Some additional questions. Which model predicts terminal velocity? Of course, this is the model which accounts for the drag force. And then, how would being thrown downward affect terminal velocity? Well, terminal velocity would be the same. However, if you throw an object downward, it will reach its terminal velocity in less time because it starts with an initial downward velocity. And if you throw an object with a higher velocity than terminal velocity, it will have a decrease in acceleration, slowing down until it reaches that terminal velocity speed, where drag force and the force of gravity are equivalent. Thank you for watching. Have a good day.